Just let me stop.
And the question is, can you all see my screen?
Yes.
Okay.
Oh,
No weird gray boxes?
no, it looks great.
Okay, great. Um, well, so as this is the last talk of 3 days of virtual talks, thank you everyone for sticking around through all of this. It's a lot of time to be on video cons. I'm going to talk a bit about differential chromatic refraction and our plans for mitigating the false detections we get in image differencing with that, and then some additional science you can do with that. Yep, back. So thought I'd just begin at the end and highlight, where this is going to, where I'm going to go in all of this. So one takeaway is that the code that does the work that I'm going to be talking about, that's all in the LSST stack right now. And all of the processing that I'm going to show results from was all done with the LSST stack. I've exercised it extensively on simulated data because I can control all of the other confounding effects in those. And in the simulated data, you can fairly easily get a significant reduction in false positives due to DCR, especially at moderate to high air mass. There are some restrictions on using it at the moment, but at the output, you also can get out some potential interesting new science that I hope I will be able to interest you in at the end. At the bottom are a few links for more in-depth reading anyone wishes to do. The DMTN 37 on the right goes through the math behind DCR and the particulars of the simulations and the corrections. The paper in the middle by Tomas Budavari et al., including myself, is an additional derivation of it and some other simulations that explore this further. And another tech note, DMTN 121, that focuses primarily on variable seeing. So just so everyone is on the same page, what is DCR? As I said, differential chromatic refraction. This occurs because we have an atmosphere. This is great for many things, but it's bad for astronomy. And there's the refraction of the atmosphere deflects the apparent location of sources towards zenith. And we generally are fine with this. There's the bulk refraction we take out in astrometric calibration, and that's not a problem. We know how to do that. The problem occurs when the index of refraction changes significantly within a single filter. And in particular, filter U and G bands, this is a problem. And there, the blue end of G band, for example, may be deflected more towards zenith than the red end. This results in two different things you can really think about with that. One is that the same object is going to be spread out. And as far as the telescope is concerned, that object really is spread out because it's been, all of this has happened in the atmosphere. So this isn't a camera effect, though you can correct for it with a camera if you put in an atmospheric dispersion corrector like HSC has. For a variety of reasons, LSST, Rubin Observatory, does not have an ADC. So that leaves it to us to fix the problem in software. The other effect that you get with this is that you can have two objects, one very red and one very blue, that in some observing conditions are going to move so that you observe them directly on top of each other, and in other observing conditions are going to move so that they are apart from each other. The particular challenge for astronomy is that the shift is, it's wavelength dependent. It depends on the inherent spectrum of your objects. And so you can't just do a single shift across your image because, each pixel is, is mapping to a different location on the sky, and that location depends on the wavelength. So the bluer photons in one pixel are truly coming from a different location beyond the atmosphere than the redder photons that land in the same pixel, even though you detect them in the same place. So the way that I think about this is, so if the whole band has significant chromatic refraction across it, break it into some smaller sub-bands. And let's assume that over those sub-bands, there isn't any DCR. Now, this is an approximation, but as with any good approximation, you can keep making smaller sub-bands and hope that it goes away. In this cartoon, I've illustrated at the very top, that's an elongated PSF due to DCR. And let's say that within 2 sub-bands of G band here, let's pretend that DCR is negligible. This isn't quite true, but for the cartoon, let's pretend it is. Then the way that you can think about this working is that you have this beautiful round PSF in your red and your blue subband of G band, and the DCR is just shifting those, is just shifting the location of the source, which is this beautiful round PSF, and it's just shifting it on the image relative to the center of the band. And because the red half is being shifted away from zenith and the blue band is being shifted toward zenith, once you add those 2 up and get the whole band, you are left with this elongated PSF. And this approximation becomes more accurate the more of these subbands you have and the narrower they are, so that the less DCR there is in them. For like the Rubin Observatory passbands, one interesting note is that U and G bands have roughly the same contribution of DCR because the U passband is narrower than the G band. So even though the effect is worse at the shorter wavelengths, the band is shorter, is narrower, and so the 2 balance each other out. This becomes much less of an effect once you get to the redder bands. Like R is very small, I it's practically negligible. Now, you don't actually know the spectrum of these objects. If you did, we wouldn't really have to go and do much more astronomy because we'd already know it. But what we can figure it out. And that's because we've taken many observations over a course of a year or several years, we'll have many observations of the same field. And each of these will have a different realization of DCR. In this cartoon, and this is a great simplification, we've got this one observation where it's being stretched up and down, and then another one where it's being stretched to the side because we just happen to have made the observations of this object so that works out. That obviously can't happen, but it's easiest for visualization. And in these cases, notice that if this is a static object on the sky, it's not moving, it's not variable, it's not changing. In the subbands, say in the redder subband at the top, subband B, it is exactly the same in observation 1, observation 2, all the way to observation N. It's just it has a different shift. Same subband A, it's the same. Observation 1, observation 2, all the way to observation N. It's just there's a different shift. The amount of the shift, that's something we can easily quantify. That's we can easily calculate how much the center of subband A should be shifted relative to the center of the full band. And so what we want to do is use this information of knowing how DCR is shifting these subbands and use the observations of the different stretched out objects to go and actually create these subband co-added images. And just like to stress, because this is a different way of thinking about some of this than many people are used to, that this is all the pixel based. So these calculations are not being done on catalogs or the objects. It's being done on coads, so the actual pixels of co-added images. The way we think about this, using a matrix formalism up here at the top, if each image S is all of the is the sum of the different subbands of the model images Y, shifted by just a pure shift matrix B. And note that if B is a pure shift, then applying the shift and applying the reverse shift gets you back the identity matrix, no change. Little cartoons below tie this into the previous slide where the S, the pixel values, that is literally the pixel values of each of those images that are elongated in various ways due to DCR. And the Y alphas, those are literally the pixel values of your model, your co-added image that you're trying to build up. And the B is just a shift. In practice, I've been using just a Lanczos 3 shift. You could use other forms of shifts depending on how accurate you wish to be and what other drivers. The way that you actually can then solve this, because this looks as though you could just then directly try to just solve this directly. Now that would involve doing a gigantic matrix inversion with a covariance matrix that is equal to the total number of pixels by the total number of pixels. That's not possible in practice at all. So the approach is use iterative forward modeling, where in the equation here in the center, where I'm solving for these Y gammas, you start out with some initial guess for what the flux in each pixel in each subband is. The good guess is make your standard deep coad with whatever flavor of coad you've heard earlier in the week you like, divide the flux by 3, if you have 3 subbands, for example, and use that as your starting point. Obviously, that's not going to be exactly correct, but it's a very good starting point for the iteration. And so for each subband, do this calculation where you are shifting all of the other subbands, holding them fixed. Apologies for the sounds in the background. My cat seems to have struck up a fight with a neighbor cat. So each subband is being shifted by its own DCR shift, and then shifted back by the DCR of the subband that you're trying to solve for. And in each case, you're holding those alphas not equal to the gamma, the one that you're trying to solve. You're holding those fixed for this iteration and iterating through each of the subbands. In each case, you're holding all the other subbands fixed. Once you have your new estimate for each of the subbands, because it is only an approximation, because you are only solving for one subband at a time, then you take those old solutions, throw them back into the equation, and iterate and iterate and iterate. And there's a variety of things you can do to try and help this converge nicely. I mentioned here that you can easily get oscillating solutions where it overshoots and then overshoots, and so you use some damping factors and other things to try and help this converge nicely. So that's the principle behind figuring out what model you're going to have in each of these subbands. So then you get a coad for, say, G band in 3 subbands. Worth pointing out that this is complicated a bit to build up this model, but once you want to use it for image differencing, this is actually very fast, because you don't have to go through this iterative forward modeling for that. You can just do that top equation where you're now shifting each of the subbands for your new science image, and that is your DCR matched template for a particular new science observation. So this has complications for computation when you're building up the model, but for, say, alert production, it doesn't seem to have extra impact. Throwing this at some simulations. So these, the top row here are some image differencing residuals where the template is a direct coad built from 8 observations where the observing conditions have been chosen using the OpSim scheduler database, so that it's a realistic distribution of parallactic angle and air mass. One caveat here is that every observation going into the building the model has exactly the same seeing. Now, this is never going to happen in real life, but it's simulation, so we can turn on new effects as we want to start dealing with them. The math that I was showing in the previous slides, that is only strictly accurate if the seeing is exactly the same in each of the observations that builds up your template. As far as science images, when you're using them, there it's no different than any other form of image differencing, and it doesn't. It's perfectly fine for the seeing to be variable there. You'll notice in these 3 examples, the seeing is different in the different science images. The DCR match template is significantly reducing the number of residuals, though it's not reducing it to 0. And that's because of a few different things. One is that I've only modeled this in 3 subbands. With 8 observations, if I made a mini subbands, then there would be too many free parameters. You really want to keep the number of free parameters down as low as possible. And also because this is an iterative procedure, you have to cut it off at some point, or else it could keep running and converging slowly to much finer levels. There might be cases where you would want to let it converge to a very high level, but in this case, I cut it off. So it is significantly reducing the number of objects that are still there in the residuals. I should point out that in these simulations, any detection is a false detection because there are no variable sources in here. And if you can see it within the images, these dipoles using the direct coads, they are pointing in different directions because those sources have different intrinsic spectrum. And so these are some of the effects that you can't take out with just astrometric calibration. So how do we handle variable PSFs? Now, there are 2 ways I'm thinking about handling this. There are more ways you could imagine to do this, but I want to highlight just these 2. First one is to try and replicate what I did in those simulations. Just really restrict the range of seeing that goes into your building up your model, and if you restrict it enough, then that will be accurate. But one problem with that is that you really need high air mass observations to help constrain your model. And those are the ones that tend to have higher seeing. So if you're restricting your seeing, then you're more likely to cut the observations that help constrain your model the most. Another possibility is to use PSF match warps. If you recall Jim Bosch's talk on Tuesday, he highlighted a number of the problems with using PSF match warps, such as correlated noise and loss of information. An additional one for DCR is that those, the PSF matching, the PSFs of each of those images is going to contain DCR in it. Your estimation of the PSF will be elongated due to DCR. And that means that you would be taking it out, you would be taking out the effect of some of the DCR and then trying to do your calculations based on that. So, but you'd be taking out not quite right. So ideally, you would want to first construct a PSF that contains everything in the image except for DCR. So that's an additional step that isn't very well thought out. But let's say that you, let's say you go with the first approach for now, because that's easy. All you do is you restrict the observations that you're using. If you do that, and this is again, all simulations, so there's nothing else going on other than, other than, well, noise is different, but the ranges of seeing and DCR are the only effects in these images. There's a lot of words on the right, in case people are particularly interested in exactly what's going on in here. I'll just highlight a few things. So there are, this is showing 4 different sets of simulations. The first, with the blue, is when the seeing of the input observations are all constant. And so then you go ahead and you build your DCR coad, and you also make a direct deep coad. Use both of those separately for image differencing. And the direct coad produces, let's say, 100 false positives at air mass 1.5. In that case, then the DCR coad is showing it will have around 20 false positives, which is a fairly dramatic reduction. But the quality of that fit of the model gets worse, as the range of seeing increases. Because as the range of seeing increases, trying to do your iterative forward modeling is less and less exact. So each one of these columns is a different science observation, and exactly the same science image is then used 8 times with 8 different templates, both the DCR coad and direct coad, and the 4 different ranges of seeing that went into the template. The point I'd like to emphasize, got it here in bold at the bottom, I said before, since there are no variable sources, so every detection is a false detection. But, and so this is reducing it quite significantly, especially for observation science images above air mass about 1.1. But even below that, it's still reducing it significantly. Now, you can get your improved image differencing with your DCR coad, but because you also have now a coad in, for example, the 3 subbands of G band. That implies that you could go ahead and do additional things that you would do on, say, GRI bands and measure colors and all sorts of things like that. So here is that simulation I was just showing, but now the 3 subbands of G-band have been turned into RGB colors just to image what the model looks like. And you can readily see the different sources really do have different colors. You see the red ones, blue ones, a few green ones. And that's because these sources all have realistic SEDs behind them, and you're able to recover that sum. We can go beyond this because we can run source measurement and see what we actually get from that. Here's a sample of 6 stars that were in that image I was just showing. The blue line is the input SED. These are just Crookes SEDs that have realistic temperatures and metallicities and so forth. And then the curve here is also multiplied by the LSST G-band throughput. And the blue X's are what you get if you bin that into the 3 subbands. Completely separately, I have run source detection and measurement on those subbands, and then just matched up the closest, then matched up those detections with the simulated sources. And so these are 6 of those examples. The red pluses are the measurements off of the subbands. And what you can see is that, well, it's not perfect. You really are recovering that spectrum that went into these sources. And you can tell the difference between different types of stars. To do this, I wanted to test more than just how we do on stars. So also that simulation also had quite a number of quasars. In fact, far more quasars than is realistic because I wanted to be able to actually see them. So here these blue curves are different quasars at redshifts taken from Vandenberg et al. And again, the blue X's are that spectrum binned into the 3 subbands. And again, you can see that it's not perfect, but you are still getting some of those features. In particular, you can see very steep spectrum here, and you're recovering the peak up a bit as well as the peak in the middle. So people have used DCR for quite a while to identify quasars based on catalogs and how the objects move in the catalogs, position errors. This is a slightly different tool. It's still making use of those position differences, but you're able to make these subband spectra measurements directly on the coads. And once again, all of this is, the only data going into this is from G-band. Those were just six objects I picked out of quasars and stars just because they were of different stellar types and quasars at different redshifts. But if you look at a wide variety of stars and quasars throughout this simulated field, you can see some of the scatter, but that scatter is all centered around the consistent value of the measured color being consistent with the true color. And because it's simulations, I really do know what the true color is. You'll notice some of the, especially down here, some of this scatter, a lot of this is due to faint sources. those sources that are close to the detection limit. If you think about that, a source that's a 10 sigma source in a standard coad, that's going to be a much lower detection in one subband, because the significance is going to be down by about a factor of 3 if you have 3 subbands. One other thing to emphasize is that I've turned off astrometric calibration in these because it's simulations. The observations that I have coming in, the images, they're in exactly the right place. So astrometric calibration can only introduce errors. So what does that look like? Because we can't do that in real life. If you, in those same simulations, now turn on calibration, you see that that introduces both a bias and slightly increases the scatter. And this is because DCR is shifting the apparent location of your calibration stars, particularly for your high air mass observations. And the DCR model tries to fix that in its iterative forward modeling. And if you have, let's say, very blue stars in your that are chosen for your calibration, then all of those are shifted more towards zenith than the rest of the objects that are not. And you'll have the center of the band incorrect shifted towards the blue. And when the DCR model is then trying to do its fitting, less flux is going to end up in the bluer end of the subbands than in the red end, because it thinks that when it's shifting things around, it'll see that there's a lot more stuff over on the red end than in the blue end. And so it thinks that everything has a redder spectrum. This is something that hopefully will get better using joint cal. These simulations were run with calibration on the individual exposures and not using joint cal. So we do have ways of trying to fix this. But it is interesting to see how the DCR and astrometric errors is easily visualized in these colors. So all of this has been in simulation, but we have quite a bit of precursor data that we can run this on. I mostly have been focusing on using the DCAM HITS survey from 2014 and 2015. I don't use HSC because they have an ADC. And so DCR is taken out. That can make a good null test, but it's otherwise, it's not interesting as far as trying to build a DCR model, because the DCR is not in the data and it's not relevant for making DCR match templates. Looking at the DCAM data can do some of the same stuff. So here is this is a color image that's made from just G-band. So there's only G-band in here, but 13 observations contributed to this particular image, and they were restricted by seeing, because that's what I have working at the moment. And those input observations range from air mass 1 to about 1.6, all from DCAM HITS 2014. And there's a number of artifacts that are plainly visible in here. Those are things that I'm working on. Like, you can see the various wings around some of these bright sources. But you can see plenty of actual colors. Many sources are very blue. You'll notice that everything has a very blue tint in here. That is almost certainly at least contributed by the astrometric errors that I was talking about in the previous slide, where if it looks as though the entire image has been shifted blueward, that's telling you something about how the DCR talked with the calibration stars. I chose this particular region of DCAM hits because it contains a number of known quasars. And we can take a look at some of those, partly for a check on whether this is performing if this is performing well. And you can notice right away, these are all very blue objects in here. I don't know exactly how blue they should be, and how blue are they compared to the other objects. That's all work that's ongoing. But you can really, there's a lot of stuff that you can just look at in there, and I think that more will be coming out of this. One thing I should say is, don't worry about the artifacts like this streak down the middle. This was data that was run back before a bug was fixed that was missing some of the compare warp masking improvements and artifact rejection. So that is all something that has already been fixed since the data that went into this image were made. Other highlights, I think, are that you can look at some of these resolved galaxies, and aside from the centers of some of them popping out, you can almost pretend that you can see other, especially bluish and reddish regions within them. Now, this is all very preliminary, so take everything that you see here and that I say with a grain of salt. These were made with the direct warps. Can also make the same thing with the PSF matched warps. Everything was done almost the same, except that instead of using the direct warps, the warps were first PSF matched to each other. There are a number of immediately obvious differences. Some of them are superficial, like the artifacts of different colors around here. I wouldn't pay too much attention to those. But you can still see a significant color difference between these quasars and some of the other objects. Looking around, you can notice some that are particularly bluer than many of the other objects in here. All of this is going to take considerably more work to understand well and get it so that it is usable. But I feel like there's quite a bit of potential there. To the best of my knowledge, these are some of this is one of the first techniques that makes use of a single band to make color images. So I'd like to wrap up there. Thank you everyone for listening. Sorry, the remote connection does feel a little bit like talking into a void, so I hope that I didn't lose your attention throughout that. So just to bring this back to where we started, I'd like to reemphasize that all of the code that made these coads and did the processing, that is all in the LSST stack. And on the simulated data, seeing significant reduction in false positives at moderate and high air mass. There's definitely more work that needs to be done, particularly in the different ways of properly handling variable PSFs. Work is ongoing on using the existing data from especially the DCAM hits survey that's being processed over at NCSA. And continue looking at whether using things like joint cal to try and improve these images, but also there's potentially using the DCR in order to evaluate the levels of astrometric errors. There's, of course, a tension a bit between stars with proper motion and DCR, because one of the main assumptions is that objects are stationary and not variable. So it will take some additional work to figure out what to do with stars that are in fact moving. And as a final note, well, nothing in principle suggests this breaks down on crowded fields. In practice, as with everything else, it is a bit harder to get everything clean and neat in crowded fields where sources are overlapping, and that is a source of ongoing investigation. And finally, point you again to the links at the bottom for further background or more details on anything that I said today. I think that is all. It looks like I'm wrapping up a little bit ahead of schedule, but thank you very much.
Thank you, Ian. Can we have a round of applause for Ian, please, on Slack? And it's okay that you wrap up ahead of schedule because you actually started a little bit ahead of schedule as well.
Great.
So we have a couple of questions already. The first one is from, or the first two actually are from Michael.
How do you deal with covariances between the subband models, both in the construction of the template itself and then actually also for the subband colors that you were showing us there?
The covariances, you mean like the noise covariances or covariance between one band and the other?
The noise covariances. I think I mean noise covariances.
Okay, well that really should fall under the ongoing investigations. Right now, what exists in the stack is that essentially just take the variance planes from the input direct coads or PSF matched coads and don't modify that, because I worry about then introducing additional covariance into those variance planes. There's clearly additional, this is introducing additional covariance, and I do not yet take that into account, no.
And then the second question was basically, you're looking at the subband models of these, but it would be nice, I guess, ideally, connecting with our conversation earlier today, to have subband, crossband models asking the question about what are galaxy color gradients and structure.
You mean not just talking about G0, G1, G2, but also going to including R0, R1.
Right. I mean, I understand for why you're preparing these templates, like that's not necessary, but it would be nice if overall we had in the science pipelines a consistent answer, check, and test about the galaxy morphology, the assumption of one morphology for all filters, right, which people are pushing back on earlier today. It seems like what you're doing is actually a very detailed way of looking at that question.
So I may be not quite following parts of your question, but let me try to answer that. So the subband coads look like just a G-band coad, except there's a little bit of additional metadata. So there isn't anything stopping someone from using existing tools to run, I don't know, something like Scarlet over the subbands of G and the subbands of R or U or something altogether. And most of the things that you can do with a standard coad, you can do with these as well.
Yep, agreed. It wasn't in some sense a question to you. I suppose it was a suggestion of one way of looking at the tests proposed earlier today.
Yes, I think there is definitely more that can be done with that. And I think that would be very interesting.
Okay, so we have 2 questions now from Wei Xian.
All right, can you hear me?
Yes.
Yes.
Okay, so I think the first question is going to be very straightforward. For the B matrix, I would assume that it's just a function of air mass and other like seeings stuff, and you can arbitrarily, you know, map from your sky model to any locations, right?
Yeah. So that all that depends on is the zenith angle and parallactic angle.
Right. So it's not being optimized. It's just like a known function. So
that's correct. So you don't need to use anything in the image to figure it out. You know, if for like an upcoming science observation, you know where the telescope is going to be pointed, or at least close enough, and you can work out what these shifts are going to be ahead of time.
All right. Awesome. The second question, I think Robert might have answered my question somewhat, but I'm curious, like in your using your reference image, is there any way, like, if not saved, like to recover the astrometric offset just due to DCR?
Do you mean you have a new image and you want to, a new science image, and you want to figure out what the astrometric offset is in that image based on what your template says?
Yeah, pretty much.
In principle, yes. I looked into that briefly a couple of years ago now, and you know, it sounded kind of easy, but in the short amount of time I had available to work on that, it wasn't exactly easy. And I haven't gone back to that. But yes, it's something you can definitely do in principle, because you're looking for coherent shifts, and you know, along the direction along the direction that you expect DCR. And so that reduces your 2D image down to a 1D problem. And it seems as though that is something you should be able to do. But as with all things, it is a little bit complicated to actually do in practice.
Okay, thank you.
Okay, Conrad.
Hi, so is this going to work if there is, for example, a northern extension out to declination 25 or 30? Because then you will be always observing at high air mass and always at pretty much the same orientation as well. So does this break down at some point?
It doesn't break down, but as you go to higher and higher air mass, you do need more subbands in order for the approximation to work. Needing more subbands means that you need more observations to constrain that. Going to some, if you have one field that is at particularly high air mass, but you come back and observe it multiple times, it should work. The region in which this does not work is if you are observing, say, within the wide, fast, deep field, and everything is under air mass 1.4, and then 6 months later, you get some target of opportunity and you zoom back there, but now that happens to be at particularly high air mass that is way outside of the range of air masses that you built the template from. This doesn't extrapolate well. So for something where you have a large set of high air mass observations, and then your science images in the future are also within that range that you've observed in the past, that works fine, but it doesn't extrapolate well.
Okay.
Okay, question now from Dan.
Hey, Ian. So I was just going to ask, are there any constraints on how the subbands are configured? And if not, could you configure them and then compare to narrowband imaging, like from the POW survey or other similar ones?
There aren't any constraints built on principle. You could choose, and it might even be wise to choose subbands that were shorter at the bluer end and wider at the redder end. That would probably make sense because the bluer end you have more a stronger DCR effect. In practice, I've simply taken the full filter passband and if there was 3 subbands, just evenly divided into 3 chunks. But that's just based on what was relatively easy to do. If you wanted to try and have a very specific subbands, you could do that. I hadn't thought of that, but yeah, you could do that.
I did just notice that POW did imaging both in broad and narrow bands, but I don't know if they have an ADC or if there are big surveys where they had no ADC and broadbands as well.
Yes, I'm afraid I don't know more about that.
Okay, so do we have any more questions? Got no more hands up. I see Robert Lupton is typing something. I don't know if he wants to ask a question or not. He doesn't, that's a thumbs down. Okay, he's just adding some comments. Okay, so if there are no more questions, let's thank Ian again for that very nice talk. And that brings us to the conclusion of the meeting. This was the last talk. And so in summary, I'd like to thank again all the speakers for their excellent presentations, especially thanks to many of you who I know who had to juggle domestic issues that have been brought on by the current world situation. I'm sure it was very difficult for you, but nevertheless, everyone persevered, and I think we had a really good set of presentations. Thank you also to all the participants for bearing with us when we made the decision 2 weeks ago to change this workshop from an in-person meeting to a virtual meeting. It was a very difficult decision at the time, but I think in retrospect it was the right one. 3 days of virtual meetings is a lot, and these are very challenging times, so thank you again for everyone's participation and continuation. Yes, Meredith, I see your Slack. I haven't forgotten about the virtual photo. I've been taking a few snapshots as the meeting's been going along. Maybe we could do that now. I think what we're asking is for everyone to turn their videos on. And I will try and take, unless anyone knows how to do this with Zoom, is to just take a snapshot of everyone with their cameras on. I guess I'll have to scroll through. Okay. Tom, you're in my, oh, I love that, Andrew. That's great. Get some babies in there as well. Who wants to bring their kids in and bounce some babies around? I'll take dogs, cats if I have to. All right. Excellent. There's, hang on, I've got 3 to take. Will, you're blank. I guess Will's probably at the status me. No, there's Will. Okay, Fed, oh, Fed's got a great dog. I love that dog. I love that dog, Fed. Josh, lovely little one. Lauren, beautiful dog. Everyone, all right. That's the second one taken. And the last one, Song. Is that a real dog? No, it's a penguin. Nice kid, Josh. All right, Matt, Paul Price, Raoul, Wei Xiang, you're all blank. Do you want to turn your videos on before I snap this? All right, we've got 3 people without videos on. Let me just check that the photos look good. Yes, I'm going to take one more again though. Hang on a second.
So while Leanne is figuring out her photos, I'm going to abuse my co-host privilege to jump here and say we should all give thanks in particular to Leanne. It has been a saga, as you can imagine, organizing this meeting, particularly with the last minute change of venue, and just trying to shepherd all the DM folks, all the community members in order to make a coherent meeting. She's done an amazing job. Thank you very much, Leanne.
Thank you, John. But honestly, I want to give a great thanks to all the speakers. I think the talks were excellent, and it's been, honestly, I was quite nervous about this meeting and how it would turn out. I have never run a virtual meeting before. I have run meetings, but never a virtual one. This was my first time, so I'm really happy at how well it turned out. So thanks to everyone. Couple more small points I want to follow. I would also like to thank, in addition to the local organizing committee at Princeton, who I thanked at the beginning of this workshop, I want to also thank Heather Shaughnessy, Regina Matter, and Richard Dubois from Slack. They, at the last minute, helped me get Zoom together, and they gave me lots of tips about how to run a meeting through Zoom, how to run a virtual meeting. It was extremely important and very helpful to running this meeting. I also want to thank Arjun Day of the DESI collaboration. They also converted to running a virtual collaboration meeting last week, and they were doing it here at Aura in Tucson. So I grabbed Arjun and picked his brains about what to do and not to do at a virtual meeting, and it was extremely helpful. Yes, Fed and everyone, I plan to write up, I plan to try to put together a short tech note about how we organized this meeting and how I ran it with all those tips, and to share that with everyone. What else do I have to say? The talks, all the talks now are linked to the agenda, and all the recordings will be linked in the live notes. I should get an email shortly about the latest links to Zoom for the talks. So they will be made available, and they will be made available fully publicly. I don't know exactly how we're going to do that yet. I think I will talk to the Rubin communications team about the best way to make sure that these talks are freely available to everyone who wants to listen to them. With this virtual meeting, one of the things that we missed, obviously, that we couldn't have, that we would have had at the in-person meeting, were focused discussions at coffee break, at lunchtime, and at unconference sessions. We do still want to find a way to have some of those more focused discussions, especially out of many of the topics that we discussed over the last few days. As I explained at the beginning of the workshop, our plan is to hold in-person sessions at the Project and Community Workshop in August here in Tucson, and we plan to invite all the invited speakers to join us at that workshop. This is, of course, assuming that the Project and Community Workshop goes ahead as an in-person meeting. I don't think any of us can really tell what's going to happen yet. We certainly hope that that workshop will be an in-person meeting and go ahead. So that's still to be decided. We also recognize, though, that that's about 5 or 6 months away, and that people would like to have follow-up discussions before then on a shorter timescale. So we are also looking at organizing smaller focused virtual meetings where we will focus just on one topic and perhaps have a more open discussion session rather than plenary presentations. Michael Woodvasey and Desk have already very kindly offered to help organize such smaller follow-up discussions around selected topics from this workshop, and to help coordinate with other science collaborations. So I will work with them and anyone else who's interested, and there will be details to come shortly on how that will happen. And finally, there will also be a written technical and scientific report from this workshop, not just about how to run a Zoom meeting, but the actual scientific aspects that we discussed. There will be some sort of written report that will be put together, summarizing the talks, the discussions, and many of the emergent topics and things that we might want to take further beyond this meeting. And that will be made available shortly after this meeting. And so that's all I have to say to sum up. Thank you again to everyone. Would anyone like to say anything before we sign off? Okay, so thank you everyone. Goodbye. Talk to you soon.
Bye everybody.